Hey everyone, and you should be able to hear me. All right. Yes, definitely. Give me a moment and we'll start. Yes, can you hear me clearly, loud and clear? Some familiar faces. Yeah, okay, perfect. Right. Okay, perfect. Yes, I hope you've seen the assignment 5 physics. Maths is coming up very soon. I can't promise that it will be out tomorrow, but most likely Thursday it will be out. So we are talking about momentum. Finally, one of the very important laws in physics, conservation of momentum. And first, I want to go through the proof of conservation of momentum. Because in school, you're not normally given like a solid proof why is momentum conserved. So that's what we'll start with. I'll share my screen. Okay. I have the chat here. If you can't see my screen, let me know, but you should be able to. Conservation of momentum. So we consider that we have three objects. This can be extrapolated to any number of objects, but we are looking at three. And these three objects, they interact with each other, and they also have external forces acting on them. So when they interact with each other, let's say M1 and M2 interact with each other. It doesn't really matter which way they are either attracted or repelled. Let's say M1 and M2 are somehow attracted. We don't know the nature of that force, but there is a force. It could be electrostatic repulsion, for example. And we label this force F12. So that means the second object is acting on the first object. Now, this force would be F21. So there is a force on M2 from object 1. In a similar way, we write the interaction between, well, let's make this interaction the other way. F21. Let's say M2 and M3 are repelled. Maybe they are colliding. We don't know that, and it doesn't really matter what's the nature of that force. So that's F23. So this is the interaction between object 2 and object 3. F32. And finally, we have, well, not finally, we have the object 1 and object 3 interacting. And let's draw that force. Okay, so this is F13, and this is F31. And there are also external forces acting on each object. Let's call it F1 external, F2 external, and F3 external. This is F1 external, F2 external. Once again, we don't know the nature of those forces. It could be gravitational force, it could be some kind of propulsion system. F3 external. Okay. And now we need to write down the Newton's second law for each of the 3 objects. So Newton's second law. Newton's second law. So for the first object, we write down that M1 A1 is equal to, oh, this is a vector, of course, is equal to F12 plus F13 plus F1 external. For the second object, M2 A2 is equal to the sum of the forces of acting on the second object, which is F21 plus F23, sorry, plus F2 external. And then we write M3 A3 equals F31 plus F32 plus F3 external. Okay, so these are the forces acting. Now, I want to add these. Three equations. And we get M1A1 plus M2A2 plus M3A3. These are vectors, equals. Now, from Newton's third law, we know that in an interaction between 2 objects, the forces are equal and opposite. And if you're adding equal and opposite forces, they add up to 0. So F21, for example, and F12 and F21 have a total of 0. F12 plus F21 is equal to 0 because of Newton's third law. And the same goes for F13 and F31. And the same goes for F23 and F32. That's 0. This is a total of 0. This is a total of 0, and this is a total of 0. So we have F1 external plus F2 external plus F3 external. Okay. Now let's work with the left-hand side. Well, MA is M1 delta V1 divided by delta T plus M2 delta V2 by delta T, because the acceleration is delta V over on delta T, M3 delta V3 on delta T, and that is equal to the sum of the external forces. The sum of the external forces. Multiplying this by delta T, we get M1 delta VI, V1, plus M2 delta V2, plus M3 delta V3. And that is equal to the sum of the external forces multiplied by delta T. Now delta T is the same for all objects because it's time. Time is the same. So it might be inside the sum. So it might be like this, or it might as well be just outside. So it's not important. The important thing is that this is delta P. It's the change in momentum of the first object. This is the change in momentum of the second object, delta P2. And this is the change in momentum of the third object. And it's equal to the sum of the external forces multiplied by delta T. Now this term, we can say that this is the impulse of external forces. Forces. And this is the total change in momentum of the system. This is the total change in momentum of the system. Total change in momentum. So therefore, I can finally write down that the total change in momentum of the system is equal to the sum of the external forces times delta T. And from here, I can say if the sum of F external, right, the sum of F external I is zero. If the sum of the external forces is zero, is the vector sum of the external forces is zero, then the total change in momentum is zero due to Pi is zero. So in simpler words, well, basically this is a fancy way of saying that in an isolated system, when there are no external forces, if in an isolated system where there are no external forces, or total external force is zero, the momentum is constant. So the total change in momentum is zero. And this is the proof of conservation of momentum for three objects. This can be extended to n objects, where n is any number, just adding more terms to it. Yes, and the proof is given in the assignment. There's a proof for n objects, but this is how it is done for three. Okay. How well do you understand this proof? Please vote 0 to 10. Oh, brilliant. Very good. So the sum of external forces is zero, then the total change in momentum is zero, and this is the proof of conservation of momentum. Impulse is a force times time. So for example, if you hit a ball, I'm going to use props today. I'm going to use props with my Christmas present. So let's say you have a golf ball and a club, and the club hits the ball. Yeah, the club hits the ball. There's a force. There's a force applied to the ball at the moment of contact, and here it is. So we have a ball, and there's a force. Well, usually it's at an angle, and the force and the impulse is the force multiplied by the time of action. Impulse is a vector, and it's measured in Newton seconds. Newton seconds, because it's Newton seconds. So impulse is force times the time of action. And sometimes the force is uneven. So if the force can change through time. Certainly it does with a golf ball. With a golf ball, the force first increases. Force increases and then decreases as the golf ball deforms. Yeah, the deformation of a golf ball, when it's hit, it squashes, it changes size. So the force increases as the ball squashes more, and then as the ball unsquashes, it returns to its original shape. The force decreases, and because this is force and this is time, now the area under this graph is going to be the impulse. Impulse is the force, well, is the area. Is the area. But also, impulse, on the other hand, is equal to the change in momentum. Impulse is also equal to change in momentum of the object. So, for example, if I give you this graph, you will know and the ball was stationary at the beginning. You will know that the momentum of the ball after impact is equal to that area. And we have a couple of questions on that, okay, where you need to calculate the area, and that gives you the impulse. Okay, moving on. Oh, and the first problem is about that. Two objects of mass m1 and m2 collide head-on. Okay, so a diagram. M1 and M2. Traveling with speed v, M2 is at rest. Okay, so M1 is traveling with speed v, and M2 is at rest. The force of interaction is given. Find the velocities of the two objects after impact. Now, the problem, like if we didn't have this graph, some would say that, well, you have to calculate you need to use the conservation of momentum. So let's try just using conservation of momentum. So initial momentum is m1 v1, m1 v. Let's say after the collision, m1 moves with velocity v1 and m2 moves with velocity v2. m1v, that's the initial momentum of the system, because this one has no momentum. has to equal to m1v1 plus m2v2. And the problem with this is that it is one equation and two unknowns. Two unknowns. Only one equation. And as you know, two unknowns and one equation usually is unsolvable, unless you can break it down into two equations. So you can't solve it. You can you could assume, for example, that the collision is elastic, but we don't know that. We don't know if the collision is elastic or inelastic. So that's not helpful. So we have to use this. We have to use the impulse. So let's calculate the impulse delivered for the two balls. So impulse is the area. Impulse is the area. So it's half base times height. So it's 1/2 multiplied by base, which is 2t0, multiplied by height, which is f0. So that is equal to t0 f0. That's the impulse delivered. Well, impulse delivered to what? Well, it's the impulse delivered to the first ball and to the second ball. As for the first ball, this impulse is going to be to the left, and for the second ball, this impulse is going to be to the right. So the change in momentum of the first ball is going to be equal to minus t0 f0, because it is hit to the left. The ball, there's a force on the ball. When the balls are colliding, there's a force to the left. And the change in momentum of the second ball is equal to t0 f0. Now, the change in momentum. So the change in momentum is the final velocity minus the initial velocity. So the final velocity, so it's m1 v1 minus m2 v2. Minus m1 v. That's the initial. That's the final. This is the initial. Equals minus t0 f0. And from here we get v1 is equal to v minus t0 f0 divided by m1. This is the final velocity of the first ball. And as you can see, the final velocity of the ball is equal to v minus, so the speed is decreased by this value. And depending on t0, f0, and m1, it could be that the ball is moving backwards. We don't know that, but the ball could be moving backwards, depending on these values. Now, for the second ball, this is the second ball, so it's m2 v2 minus the initial momentum. The initial momentum is 0 and is equal to t0 f0. So from here we get v2 is equal to t0 f0 divided by m2. Okay. So this is somewhat an unorthodox problem, because normally you're given the final velocity of the two balls and you just use conservation of momentum, but here you need to use impulse. Hopefully if you understand how I used impulse in this question, please let me know. Please vote again. If you have a question, please do ask. So how well do you understand how I used impulse in this problem? Please type a number from 1 to 10. For P1, because the force is to the left. The force pushes the ball 1 to the left in the opposite direction to the movement. That's why it's negative. And just one more thing, because these are internal forces, look what happens if I try to do delta P1 plus delta P2 is equal to minus T0 F0 plus T0 F0, which is 0. The total change in momentum is 0. This is just another, well, consequence. The overall impulse is 0. This is the graph of force versus time, and both balls experience the same force because they are interacting with each other, and according to Newton's third law, it's the same force. So this bit is a consequence of Newton's third law. Newton 3. The final. Please, can you explain why it's necessary to do final minus initial? Or well, because the change in momentum. But the definition of change, for example, if you have delta V, that literally means V final minus V initial. If you have delta P, it's P final minus P initial. Does that answer your question, Thomas? Okay. It's by definition. Whenever you see delta, you need to think of it as final minus initial. So should I write this down here just as an extra thing? So P1 final minus P1 initial, P2 final minus P2 initial. Okay, I'm sometimes losing the arrows because at some point I'm just making projections. So I have an axis here. I have an axis here, and at some point I'm I'm not using vectors, I'm using projections of vectors. Hence the negative. So I'll just remove the vector sign here. It's not necessary because yeah, I'm working with projections of vectors onto the x-axis. Okay. Now I have to say these problems are generally a tiny bit harder than the stuff in the assignment. So that is good news for you, I guess. So problem 2, a spaceship before detachment of stage 2. So a spaceship usually consists of several stages. The third stage is where you put the astronauts and satellites and everything. Spaceship before detachment of stage 2 had velocity v. After detachment, the velocity is 1.01 v. Okay, so we can assume that there's kind of a spring mechanism it could be a rocket booster, but the beautiful thing about the conservation of momentum, so that is doesn't matter. The nature of the force does not matter. So this is stage 1. This is the front of the rocket. And let's say there's some kind of spring mechanism that pushes them apart. So this is stage 1, and this is stage 2. Stage 2. And they're flying through space at velocity v. So initially they're both traveling with velocity v. After detachment, the velocity. So what I like to do is I like to draw before and after. So before detachment and after detachment. And just gonna copy that. After detachment. This goes with velocity 1.01 v. 1.01 v. And the second change moves velocity v, but it's relative to the ship, relative to the, or to the front, to the first stage, basically. That means that the velocity is 1.01 minus 0.2, so 0.97 v. Okay, relative to the ship. If you don't understand why it's 0.97 v, please let me know now. Don't be shy, it's okay not to understand, because it's the relative speed. Okay. All right. Good. And now we can say the total mass of the ship is m0. Okay, this is m0. M0. Let's call this m1, and let's call this m2. So m2, m1. So the total momentum before, so p, well, I'm gonna because they're the wrong way around. P2 plus P1 before equals P2 dash plus P1 dash. Okay, so P2 is M2 V plus M1 V, and after it is M2 times 0.97 V plus M1 times 1.01 V. And you can notice that we can divide by V. So the initial velocity doesn't matter. So M1 plus M2 from the first one is equal to M2 times 0.97 plus M1 times 1.01. Okay, and from here, I take this to the left, I take this to the right. I get 0.03 m2 equals 0.01 m1. In other words, m1 is equal to 3m2. 3m2. So the first stage is 3 times heavier than the second stage. And now we just need to do some magic with maths to work it out in terms of m0. So just a reminder for you, problems where the problems where you're not given any values, you need to assume that this is known. This is known. But any other values are not known. Well, V is known. Yeah, V is known and M0 is known. But M1 and M2, you can't assume that you know them. So you have to express them in terms of something you already know, which is M0. So we know that, well, there are different approaches. I mean, by simple observation, you can already tell that M1 is a quarter of M0 and M2 is a quarter of M0 and M1 is 3/4 of M0. But you can use a more mathematical approach if you wish. But so M1 is 3/4 of M0 and M2 is a quarter of M0. If you want a mathematical approach, you need to do M1 plus M2 is M0 and M1 is 3m2. And so by solving this system of equations, you arrive to the same point. And that's the answer. The answer must be given in terms of something that you know, or something that is given in the question. And the thing is that whatever m0 is, we can solve it. You just need to substitute. Any questions? Any questions about this? So the conservation of momentum is here. This is the important bit. Conservation of momentum. Okay, sure. Good. Now, this goes into the assignment is split into several sections. So this would go into the explosions section. Is when you have two objects, they're stuck together, and then something happens, they start flying apart. So this is classed as an explosion. The next bit is actually an inelastic collision. Inelastic collision. All right, so a proton is fired with speed v directly at a helium nucleus. Find the velocities of both particles when the proton is at closest approach. Okay, so there's lots of things happening here. If you know the gold foil experiment, and you should know the gold foil experiment, it's unlikely that you don't. You have a heavy nucleus of gold with a charge of plus 97, I believe. Okay, don't quote me on that. Well, it's a heavy charged nucleus, and there's an alpha particle with charge plus 2. And this goes Okay. It flies towards the gold nucleus and then rebounds from the gold nucleus because of the electrostatic force. Now, if it's a head-on collision, as it is in our question, if it's a head-on collision, then it will just go back, goes to the gold nucleus and then travel back. And the closest approach is when it's here, and then this distance between them, usually between the centers, is called the closest approach. So that's the idea. So what's happening? You have a proton with mass m. What would the mass of a helium nucleus be? Somebody help me. If the mass of the proton is m, yeah, 4m, absolutely. 4m. For the purpose of this question, 4m is more than enough accuracy. So this is before this one is stationary. This one is stationary, and this one is flying at velocity v. This is flying with velocity v. Find the velocity of the particle where the proton is at closest approach. So what we need to understand that when they are at closest approach, their relative velocity is 0. The relative velocity is 0. So at closest approach, when they are the closest to each other, they will be flying together with the same speed. So because of the electrostatic force, this particle is pushed to the right, and this particle is pushed to the left. So this one slows down, and this particle accelerates. And when they have equal speeds, that means that they are stationary relative to each other. So they both travel with the same speed. V, or let's call it V1. No, sorry, V1. How well do you understand why they travel together? Can you please vote? Please vote. How well do you understand that they both travel with the same speed? Okay. Well, imagine we are holding this ball. So I'll spend some time explaining. Imagine we're holding it, and here it is. And there's another ball. I don't have a smaller one. Sorry. So this one goes closer to it, and then it repels. This is only when we can neglect the movement of this one. If this one is 700 times heavier than this, that's perfectly acceptable. It comes close and then repels. But the problem is that when they come close, this ball starts moving. And what happens is they come close, and then they rebound. And the moment of the closest approach is this, that they're moving together with the same speed before separating again. So at this moment in time, so it goes, I'll try this again. So Yeah, and they both continue moving, but when they are closest to each other, they have to have the same speed, because that's the moment when this particle, this one, becomes slower than this one, and this continues traveling. Or when you have two pool balls, two billiard balls, two snooker balls, is one hits the other, one flies. There is a moment, there's a brief moment in time when they are both traveling at the same speed. Okay. So in a collision like that, if you draw the velocity of the velocity of the proton. Let's start with the proton is moving with velocity v. Then when it gets close, this is the proton. It starts off with velocity v, and this is time. Then when it reaches close to the alpha particle, it starts to decelerate. And well, because it's 4 times lighter, it would actually go backwards. At some point, it will start traveling backwards. Now, for the alpha particle, it was stationary. It was stationary. But when this starts to slow down, this starts to speed up. It speeds up to a certain value and then continues traveling. So this is the alpha particle. And this is the proton. So if you look at the proton travels and then slows down and then rebounds. The alpha particle is stationary and then starts to accelerate because they kind of hit each other. And the closest approach happens when they have the same speed. So at some moment in time, this is a brief moment. This is like an infinitely brief moment in time when they both travel with the same speed. So this is the closest approach. Okay. Can I get another vote? Do you understand now why they're traveling? Ah, really brilliant. Okay. That's lovely. So looking at these two separate moments in time, we write the conservation of momentum. So the total momentum P1 plus P2 is equal to momentum P1 after plus P2 after. And of course, this is a single equation. So this is mv plus 0, because this is stationary, is equal to P1 to mv1 plus 4m v1. And well, m cancels. And m is not given to you. So it actually works out fine. And so v is equal to 5 v1. So v1 is equal to 1/5 of v. So v1 is the 1/5 of the initial velocity. So at this moment, and in the assignment, there's a question about Baron Munchausen, which rides a cannonball. And this is exactly the same question. I mean, it is an inelastic collision. So it's a 5th m. It's a 5th m. Okay. In case of the baron, it's one of the examples. He jumps onto the cannonball, and the cannonball slows down because of that. So that's exactly him. The mass of the moving system increases 5 times here, so the speed decreases 5 times. Right. The next question is I would say very unorthodox question. Nothing like that in the assignment, but I thought that it would be very useful to go through that. So you have 2 charged particles, A and B, have mass 2m and m, respectively. So this has a mass of m, this has a mass of 2m. They have equal but opposite momentum. So their momentum is the same. So this is P1 and this is P2. So this is not velocity, it's momentum. When T is 0, they are in positions shown. The trajectory of particle B is given. Draw the trajectory of particle A. Now, this is, well, certainly is an interesting one. So we can see that so what can we gather from this diagram? Well, first of all, we know that the particles have the same charge. Oh, did I say 1/2 on 5m? Sorry. Of course, it's 1/5 v. V is the initial velocity. Sorry. So they have equal momentum. But if they have equal momentum but different mass, that means A is traveling twice as fast. A traveling twice as fast. A travel twice faster than B. Then the second of all, the total momentum is 0. Total momentum is 0 because A has momentum to the right and this has momentum to the left. That means A and B will always at any point of time travel in opposite directions. A much harder question would be, do you think A and B would retain their speeds throughout the flight? Well, we know that they will always travel in opposite directions because of conservation of momentum. They will always have equal but opposite momentum. So at any point in time, they will be traveling in opposite directions. The question I want to ask, would they travel with the same speed throughout the process? What do you think? And it's a difficult question. It's a difficult question to answer, but what's your idea? I'd like some feedback, guys. What do you think? You can guess. better if you no. Okay. So why do you think no? Or is just or is it a guess? Well, to answer this question, we can use the extreme case scenario. Considering extreme case scenarios is incredibly useful. The extreme case scenario would be that they collide head-on. If they collide head-on, that means that they're not changing direction. They are getting close and then flying apart. So their velocity is always opposite. So they're traveling closer and then opposite. They're traveling apart, closer and apart. So, but the speed clearly is not conserved. So what happens to the kinetic energy then? What happens to the kinetic energy of the particles as they approach? I mean, obviously they have kinetic energy, but where is that energy going? Because after all, they will be flying in opposite directions and the kinetic energy will be conserved. So the kinetic energy at the start is equal to the kinetic energy at the end. Okay, that much I can tell you. But what happens to the kinetic energy when they are close to each other? Stored as static, of course. Yes, it's the potential energy of the electric field, of course. There is a formula for that, for the potential energy. Of course, when they get close, there's potential energy stored between them. Then they release that stored energy when they fly apart. Basically, if they will always fly in opposite directions. So a few things. First of all, because A is traveling twice as fast, by the time, so B travels more or less in a straight line for this distance. So A would travel twice as far. A will travel twice as far before starting to curve. That's the first thing that we definitely know. Then as it curves, we can roughly split the trajectory into several parts. So let's say 1, 2, 3, 4. And because this is traveling at the same rate, it would be, well, 8 of those. So we'll start to curve 1, 2, 3, 4. So where at this moment in time, it's traveling like this. So this will be traveling like this. Okay, I'm a bit off. Then at this moment in time, it's traveling like this. So 3, 4. So it's traveling like this. So this moment in time. And this moment. So let's say that this is t equals 0, t equals 1, 2, 3, 4. 0, 1, 2, 3, 4. So at 4, it's traveling more or less this way. So this is traveling, at this point, it's traveling this way. So this is the trajectory. Okay. So this is 4. So 1 it's traveling to the right. This one is traveling to the left. 2 is traveling this way. So this one is traveling this way. 3 is traveling directly downwards. So this is traveling directly upwards. And 4 is traveling that way. So it's that. This is not an exact picture, but this gives you an idea. You can see that clearly the radius of this path is bigger because it's traveling faster. And at any point, they're traveling in opposite directions. And you can roughly break down the path into sections of approximately equal time and work out the approximate velocity in each point. Of course, you can actually do the calculations and actually write down an integral to calculate, but that would be an overkill. And so some sort of these questions are actually what you see in a bubble chamber, for example. There's lots of things. So if you don't know about bubble chambers, do read on the topic. It is year 13 physics, but you can always start a little bit earlier to read about those things. The trajectories of charged particles. Right. Any questions here? Any questions here? The ratio of velocities is constant. Or the ratio of speeds. Also, it's incorrect to say ratio of velocities, ratio of speeds. Speeds is constant. And in terms of at the end, it will be moving with the same velocity. So it's 2v. And this one would be traveling at speed v. This is v, 2v, and this is v. Okay, problem 5. A trolley of mass m and length L contains a liquid, mass m in the left cylinder. So all of the liquid is in the left cylinder. Okay, so that is that. The tap is opened. Find the displacement of the trolley once the liquid levels out. Okay. So what's sort of going on here? If we forget about the existence of the second cylinder, the picture would be quite easy, because what's going on is you have water rushing out, and that means that rushing out of the nozzle. And if this thing had wheels, and it does, it will start moving to the left because the momentum is conserved. So initially you have 0 momentum, and then this the water is pushed through the pipe. This means the water gains momentum to the right, and the trolley must gain momentum to the left. So if this is the momentum of the water, this is the momentum of the trolley. Okay, conservational moment. So we understand why we would expect the trolley to start moving. Now the problem is that it won't move very far, because at some point well, first of all, the water level will level out and it will stop moving. But as the water decelerates through the pipe, as the water decelerates through the pipe because the pressure evens out, we have the opposite effect. So it will be slowing down. Okay. So the water would be pushing through the pipe against this mass of water. So it will level out. Of course, friction can be ignored in this case. And this should be familiar to you. We've done a couple of questions like that. We've talked about the boat. So this is a question about the centers of mass. I forgot to mention that the cylinders can be considered thin compared to the length in the left. Thin the cylinders are thin compared to the length of the trolley. That's an important thing to say. So once we've established why it starts moving in the first place, because of conservation of momentum, now we can use centers of mass, of course. And to use centers of mass, we are going to draw the x-axis. And for simplicity, I'm going to say that this is 0. Yeah. As I said, the length of the trolley. So this is the length of the trolley, L. Now the cylinders are small, so we consider them at the edges of the cylinder. And there's a mass of water M present here. And the center of mass of the trolley is here. Well, here probably. Center of mass of the trolley is somewhere here. And the position of the center of mass is L over 2. This is 0, and this is L. So before tap is opened, the position of the center of mass is M1. So the mass of the water times the position of the water times 0 plus the mass of the trolley times the position of the trolley times the position of the trolley, which is L over 2, divided by the total mass of the system, which is M plus M. And we can calculate that, and it's equal to ml divided by 2 multiplied by M plus M. That's the center of mass of the trolley and water before the tap is opened. So ml divided by 2 M plus M. Now, after tap is opened, after the system returns, after the tap is opened, and the system settles. The position of the center of mass, equals, well, we can assume, let's say the trolley has moved to the left a distance of L small. actually, why not just say x? So the system has shifted to the left a distance of x, but then because the water will be even out, the water would be completely even. In both cylinders, there will be the same amount of water. So the center of the mass of the trolley and the center of mass of the water would be in the middle. Okay? So the position of the center of mass and the trolley has shifted to the left, x meters to the left. So they would be in L/2 minus x, both of them. L/2 minus x, sorry, L/2 minus x. Does that make sense? Does that make sense, guys? So the center of the trolley has moved a distance of x to the left. But once the system is even, the center of mass is the center of the trolley. So the new center of mass is going to be L/2 minus x. Yeah, does everybody understand this? I want everyone to be on board with this. Okay. Yeah, so because the system would be completely symmetrical, it has just shifted to the left. And we know that this must be the old center of mass. The old center of mass and the new center of mass is at this have to be the same. So we just solve for x. So x is equal to L/2 minus ml over 2m plus m. Okay, it's not as elegant as I had hoped, but 2ml plus 2ml minus ml. Oh, you don't need the 2, sorry. No. Minus ml divided by 2m plus m, 2m plus m. ml cancels out, and you get ml over 2m plus m. This is the distance the trolley moves. And as a matter of fact, it just moves the distance that is equal to the distance from the center of the trolley to the original center of mass. So if the center of mass originally, if the center of mass is here, the center of mass is here, the trolley would move such that the center of mass is here. So the center of the trolley would move to the center of mass. This is, yeah, and this is quite beautiful, I believe. You see, if you were because then you would need to calculate the width of the cylinder. Then to calculate the center of mass, you can't take L. You have to take L minus the diameter of the cylinder. It's just a simplification. So if the cylinder was diameter d, the center of mass of that cylinder would be d over 2, And this one would be L minus d over 2 instead of 0 and L. Does that answer your question, Edward? Yeah. It's like asking what is the distance between the Earth and the Andromeda galaxy? And you ask the question, well, which part of the Earth? Is it from the ground or from the center of the Earth? As the distance is what, thousands of light years? Or hundreds? Okay, I don't remember the distance of the Andromeda galaxy, but it's many light years away. It doesn't matter where you measure from. The Earth is small compared to the distance, so you don't bother with subtracting the rate or adding the radius of the Earth. If you're talking about the International Space Station, then of course you have to consider from which point. Like if you're measuring the distance from the Earth to the space station, you have to consider which part of the Earth are you talking about, the center of the Earth or the surface of the Earth. But in this case, it's just two thin cylinders and then the distances can be calculated. And the last question, this is from Pat 2013. This question did not make it into the assignment because it contains kinetic and gravitational potential energy, which I didn't want to add, just for clarity. Projectile of mass 0.2 kilograms, 0.2 kilograms, speed of 122 meters per second, 22 meters per second. Hits a ball of mass 12 kilograms, hanging on a massless string of fixed length as sketched in the figure below. The projectile is moving at the height of the center of the ball. So if you draw a line through the center of the ball, okay, and after the hitting the ball stops inside the ball, becomes stationary with respect to the ball. So it's a somewhat similar to the thing we did with the proton and the alpha particle. What maximum height of the ball which will reach above its original position? So it is hit centrally, because if it doesn't hit centrally, the ball will start rotating and a lot of the kinetic energy will go into the rotation. So this is an inelastic collision. Elastic collision. Because the ball, so projectile is stuck. If it was an elastic collision, then the projectile would bounce back with the same speed, well, or approximately the same speed. Okay, so we need to calculate. So we can't just say, oh, let's calculate the kinetic energy of the projectile, and then that will give us the gravitational potential energy of the ball when it rises. But no, that it's not true, because some of the kinetic energy goes into heat when they collide. When they collide and stick together, there's heat released. Therefore, you cannot say that we can't just use kinetic energy for calculations. We will need to do that eventually. So before collision, collision. So the bullet, the projectile has mv, well, let's say mu plus 0 equals to. Now, after the collision, they move together with the same speed. So it's going to be mv plus mv, capital MV. So from here, you can work out that v is equal to the final velocity of the ball, final velocity of ball and stuck projectile, that v is mu divided by m plus m. And of course you can calculate the speed at this point. Because you know the mass, you know the initial, you know all the values, so you can actually calculate it. I'm gonna leave it. I'm gonna leave it, and I'll do the substitution at the last minute. So what happens is that the ball swings and reaches a new height, and you need to calculate how much it raises above the original height. We can measure from, usually it's measured from the center. Okay, let's not confuse ourselves and actually measure from the center of the ball. So this is the center. This is the new position of the center, so we need to find the height. Okay. Another interesting thing would be to know the angle, but they're not asking for the angle. But if you want a challenge, let's assume this is length L and find theta. It's not hard, but it's not as easy as you think. Anyways, you need to find the height. So you use conservation of energy. Conservation of energy. So the kinetic energy of the ball just after the collision. So the kinetic energy of the ball and small mass, 1/2 m plus m, because they're moving together with the same speed, times v, the velocity that we have found in the previous one, squared. And it has to be equal to m plus m gh, because that's the kinetic energy, mgh. So 1/2 mv squared has to equal to mgh. Instead of m, I'm using m plus m, because that's the total mass of the projectile and ball. And you can see that we can cancel out, m plus m cancels, so, and we multiply it by, well, we need h, so we get v squared over 2g equals h. And I'm just going to rewrite this, v squared over 2g, where v squared is the velocity after the collision. It's not the final velocity of the ball, because the final velocity of the ball is 0. So we have the velocity of the ball after the collision, which is v. Let me just draw this again. So we have the ball we have the projectile hitting the ball. I mean, yes, I'm doing before and after. Before, I've mirrored the image just so that it moves from left to right. So it travels with the velocity u. This has 0 velocity, and after the collision, so the bullet is inside, so they have a mass of m plus m, and it's traveling with velocity v. Yeah, just to be clear what I'm talking about. So the kinetic energy is 1/2 m plus mv squared, and the gravitational potential energy at the top when the ball has stopped is that. So from here, I just need to substitute v squared. So it's going to be m squared u squared divided by 2g m plus m squared. You don't have to use this method, but I like to keep it neat until the very end in letters. M squared, this is the small m, so 0.2 squared multiplied by u squared, which is 122 squared, divided by 2 times 9.81, and m plus m, which is 0.2 plus 12. Okay, let's make it 12 plus 0.2. 0.2 squared, and this is something. You get 0.2 squared multiplied by 122 squared divided by 2 times 9.81 times 12.2 squared. Okay, 0.2 meters, 0.204 meters. So 20 centimeters, 20.4 centimeters. 0.4 centimeters. All right, any questions here? Okay, then if there are no questions, or perhaps somebody's typing. It's great to see you. Great to see some familiar faces. Please do keep coming. And yes, please do keep coming. And Obaid, I reply to your messages. I saw your message. I will reply. Sorry for it's taking me so long. Okay, welcome. See you, everyone.
Can I just ask a quick question?
Yep.
How did you know that when like the projectile got stuck into that ball? How did you know that the collision was inelastic?
That's the definition of of a perfectly inelastic collision. A perfectly inelastic collision is where the objects get stuck. Objects get stuck together. Okay. So imagine a wall. Yeah. Can you still hear me?
Yeah, I can hear you.
Imagine a wall, and you're throwing a tennis ball at the wall. The tennis ball bounces back. The slower the rebound speed, the more kinetic energy has been lost. Okay. The ultimate loss of kinetic energy is when the ball sticks to the wall. That means all kinetic energy has been lost. Well, it has been transferred to thermal, of course, not lost. Does that make sense? And an
Yeah, I
elastic
get it.
collision, when you perfectly preserve the kinetic energy, so when the ball bounces back with the exact same speed, that means no kinetic energy is lost. And the same can be applied to objects which move relative to another. So the wall is a simple example because it's not moving. But if they stick together, that means you have lost the maximum possible amount of kinetic energy. Okay. All right. See you next week.
Thanks.